the paradox at the heart of everything. Stand outside on a clear summer day, and the sun will burn the back of your neck within minutes. You can feel it from 93 million miles away. That persistent, penetrating warmth that climbs through glass, soaks into pavement, and makes the air above a parking lot shimmer and blur. The sun is not a subtle thing. It is a nuclear furnace 400,000 times more massive than Earth, and it has been roaring for nearly 5 billion years with no sign of stopping. Right now, at this very moment, it is converting 600 million tons of hydrogen into helium every single second, releasing energy so immense that the figures involved have long since ceased to mean anything to the human brain. The sun emits more energy in a single second than all of humanity has produced through every source, every coal plant, every campfire, every nuclear reactor, every photovoltaic panel, in the entire span of recorded civilization, multiplied by a factor that strains even scientific notation to express. And yet, just beyond the thin shell of air that wraps around our planet, it is almost inconceivably cold. The background temperature of space, the temperature you would register if you took a thermometer into the void between the stars, far from any planet or sun, sits at roughly minus 270 degrees Celsius. That is about a quarter of a degree above absolute zero, the theoretical floor below which temperature cannot drop, the point at which atomic motion ceases entirely. Space is, for all practical purposes, as cold as anything in the universe can ever get. How can both of these things be true simultaneously? How can the most powerful object in our solar system be pouring energy in every direction, while the space through which that energy travels remains essentially frozen? The sun's light takes 8 minutes to cross the distance between our star and Earth. For every one of those 8 minutes, the radiation is moving through a region so cold it would kill an unprotected human in seconds. And yet, that same radiation arrives here warm enough to sustain the most complex chemistry the universe has ever produced. This is not a paradox that dissolves easily. It is one of the most fundamental questions you can ask about the physical world. And the answer cuts to the heart of what heat actually is, how energy moves through different environments, and why life on this particular planet is possible at all. But the answer does not stop there. It leads somewhere genuinely unexpected, to a mystery at the surface of the sun itself that has confounded solar physicists for more than 80 years and remains unsolved to this day. It leads to the faintest whisper of radiation left over from the birth of the universe, cooled across 14 billion years of expansion to a temperature barely above nothing. And it ends at a question about how everything in the cosmos will eventually die, not in fire, but in a cold so absolute and final that the word cold becomes inadequate. What heat actually is. Before the paradox can be unpacked, a distinction has to be made that most people have never had reason to think about carefully: the difference between heat and temperature. They feel like the same concept because in daily life they almost always go together, but they are not the same at all. And confusing them is precisely what makes the question of cold space so puzzling in the first place. Temperature is a measure of how fast the particles that make up a substance are moving. In a gas, temperature reflects the average kinetic energy of the molecules bouncing around. In a solid, it reflects how vigorously the atoms are vibrating in their fixed positions. When something is hot, its particles are moving fast. When something is cold, they are moving slowly. At absolute zero on the Kelvin scale, minus 273 degrees Celsius, molecular motion approaches a theoretical standstill. the atoms would still possess a small residual energy due to quantum effects, a phenomenon called zero-point energy. But they would be as motionless as matter is ever permitted to be. Temperature, in other words, is a property of matter. It describes the internal kinetic state of whatever substance you are measuring. It cannot meaningfully be assigned to a vacuum, because there are no particles in a vacuum to have a temperature. Heat, on the other hand, is not a property of an object. Heat is energy in transit. More specifically, it is what happens when energy moves from one object to another because of a temperature difference between them. When you put a cold spoon into a hot cup of coffee, heat flows from the coffee into the spoon. Not because the coffee has heat stored inside it, like water in a bucket, but because the fast-moving molecules of the hot liquid are bumping against the slower-moving molecules of the cooler metal and transferring their energy. Heat is a process, not a substance. This distinction was not always understood. For much of the 18th century, scientists thought of heat as a material fluid called caloric, which flowed from hot objects into cold ones, the way water flows downhill. The caloric theory was displaced in the 19th century by the mechanical theory of heat, which recognized that temperature is simply a macroscopic expression of microscopic motion. For heat to flow from place to place, it needs one of three physical mechanisms. The first is conduction, which requires direct physical contact. When you grasp a hot pan, heat moves from the pan to your hand, because the molecules of the pan are vibrating rapidly and transmitting that motion to the molecules of your skin through collision. Good thermal conductors, metals in particular, have molecular structures that allow this energy to be passed along very efficiently. Poor conductors, like wood or air, do not. Heat conduction requires that the two objects involved are touching, or that they are connected through a continuous medium. The second mechanism is convection, which requires a fluid, a liquid or a gas, to physically carry thermal energy from one location to another. When a radiator heats a room, the air in immediate contact with its surface warms, expands, becomes less dense, and rises. Cooler air from elsewhere in the room flows in to replace it, and is in turn heated, establishing a circulation pattern that gradually distributes warmth throughout the space. Ocean currents work the same way, transporting heat from the tropical regions where the sun delivers more energy per unit area toward the poles, moderating climates across thousands of kilometers. Convection requires a fluid medium to exist in the first place. Without it, there is nothing to carry the energy. The third mechanism is radiation, and it is fundamentally different from the other two. Radiation does not require any medium whatsoever. Energy is emitted by a warm body as electromagnetic waves or photons, which travel at the speed of light through whatever they encounter, including a perfect vacuum. The sun transfers energy to Earth entirely through radiation because there is nothing but vacuum between them. An infrared heater in a cold room warms objects directly by radiation, even before the surrounding air has had time to warm. Every object with a temperature above absolute zero emits thermal radiation, and the rate at which it does so increases steeply with temperature, a relationship described by the Stefan Boltzmann law, which states that the power radiated by an object scales with the fourth power of its absolute temperature. Double the temperature and the radiated power increases not by a factor of 2, but by a factor of 16. In the everyday world, all three mechanisms operate simultaneously and constantly, which makes their individual contributions hard to separate by casual observation. Our entire lived experience of heat involves conduction, convection, and radiation working together. This makes the everyday world profoundly misleading when it comes to understanding space, because in space, only one of these three mechanisms functions, and it functions in a way that does not distribute warmth through the empty void. Why space is left out. The vacuum of space is not the partial vacuum inside a thermos or a light bulb. Interplanetary space is emptier than anything that can be created in a terrestrial laboratory. In the space between Earth and the Sun, there are perhaps 5 to 10 atoms per cubic centimetre, mostly hydrogen and helium, plus a smattering of heavier elements and electrons, collectively called the solar wind. The best laboratory vacuum chambers on Earth still contain many millions of molecules per cubic centimetre. By comparison, space is extraordinarily empty. This extreme emptiness means that in space, both conduction and convection are effectively impossible. There is nothing to conduct through, no continuous solid or liquid medium. There is nothing to convect with, no fluid to expand, rise, and carry warmth from one place to another. The only mechanism by which energy can travel between objects in space is radiation. And radiation does not heat empty space. It heats only the objects it strikes. Consider what happens when a photon leaves the sun's surface. It is traveling at the speed of light through a medium that is essentially nothing. There is no air to warm, no fluid to heat, no solid to conduct through. The photon carries energy, but it deposits none of it until it strikes something. If it strikes a planet, it heats the planet. If it strikes a spacecraft, it heats the spacecraft. If it strikes nothing, if it travels outward through the solar system and eventually into interstellar space and beyond, as the vast majority of the sun's photons do, it never deposits its energy at all, and the vacuum through which it passes is unaffected. The photon simply carries on, its energy intact but undelivered, until it eventually encounters matter somewhere in the universe. There is also something worth dwelling on in the scale of the emptiness involved. The solar system is not just large in the way that continents or oceans are large. It is large in a way that requires reframing the meaning of distance entirely. If the sun were the size of a basketball placed in the center of a football field, Earth would be the size of a grain of pepper at the far end, and the space between them would be entirely empty. Jupiter would be a marble placed about 100 meters from the basketball. Neptune would be a tiny pea somewhere off in the parking lot, perhaps 300 meters away. And the nearest star, the Alpha Centauri system, on this scale would be located not at the edge of the field or the parking lot, but roughly in another city, thousands of kilometers distant. The space between is not just empty, it is empty at a scale that makes the word empty feel inadequate. Every cubic kilometer of that space contains, on average, fewer atoms than the best vacuum achievable in any terrestrial laboratory. There is nothing to be heated. There is nothing to carry warmth from the basketball sun to the pepper earth except the radiation that travels at the speed of light across 150 million kilometers, depositing its energy only when it finally strikes something physical. The energy exists, the radiation is real, but the space it moves through absorbs none of it, is changed by none of it, and is warmed by none of it. It is one of the most counterintuitive realities in physics, and one of the most important for understanding everything else about the thermal state of the universe. The sun's journey from core to surface. To appreciate the full strangeness of the temperature situation, it helps to follow the sun's energy from its source. At the core of the sun, conditions are extreme beyond easy comprehension. The temperature reaches 15 million Kelvin, and the density is roughly 150 times that of liquid water. Under this pressure and temperature, hydrogen nuclei, protons, are forced close enough together that the strong nuclear force can act between them, fusing them into helium. Each fusion reaction releases a small amount of energy as gamma rays, the highest energy form of electromagnetic radiation. This is the primary process by which the sun generates its power, and it has been running continuously for approximately 4.6 billion years. But those gamma rays do not shoot immediately outward into space. The interior of the sun is so dense that a photon of light can only travel a fraction of a millimeter before it is absorbed and re-emitted by another particle. The direction of re-emission is essentially random, so the photon's journey from the core to the surface is not a straight line, but a meandering, stuttering random walk through plasma so dense that progress is almost unimaginably slow. The best current models estimate that the energy produced in the core takes somewhere between 10,000 and 100,000 years to work its way out to the surface. During this journey, each photon is absorbed and re-emitted so many times, and the original high-energy gamma-ray photons are scattered and divided among so many lower-energy photons, that by the time the energy finally escapes the sun's outer layers, it has been degraded from fierce gamma radiation into the gentler mix of ultraviolet, visible, and infrared light that we observe from the photosphere. The photosphere itself, the visible surface, the thin layer from which most of the light we see is emitted, sits at around 5,800 Kelvin. It appears to us as the sun's sharp edge, though it is not truly a surface in the way a rock has a surface. It is the depth at which the solar plasma becomes opaque to visible light, where the density is just high enough that photons cannot escape directly outward without being scattered. Below this boundary, light is trapped and diffused. Above it, photons travel freely. This opacity boundary is what gives the sun its appearance of having a well-defined edge, and it moves slightly inward and outward with the 11-year solar cycle as the sun's activity changes. What the sun radiates from the photosphere is primarily visible light. No coincidence, since life on Earth has evolved over billions of years in the presence of this specific spectrum, and our eyes are tuned to it precisely. The sun emits across a broad spectrum, from ultraviolet through visible into infrared and beyond, with the peak of its emission falling in the green wavelength range. The mix of wavelengths across this spectrum is what we perceive as sunlight, warm, bright, and broadly illuminating. Different components of this spectrum interact differently with Earth's atmosphere. Ultraviolet is largely absorbed by the ozone layer. Visible light passes through relatively unimpeded, and infrared radiation is selectively absorbed by greenhouse gases. The specific mix of the sun's radiation and Earth's atmospheric response to it shapes the entire energy budget of the planet. Above the photosphere, however, something deeply strange occurs. Instead of continuing to cool as distance from the nuclear source increases, the temperature of the sun's atmosphere begins to rise. First through the chromosphere, reaching around 20,000 Kelvin, and then dramatically through the transition region and into the corona, where temperatures spike to 1 million Kelvin and beyond. This observation, and the mystery it represents, is one of the central stories in modern solar science. What the numbers actually say. The coldness of space and the heat of the sun are not abstract concepts. They are measurable quantities, and the measurements reveal just how extreme the contrasts are. The sun's surface radiates at 5,800 Kelvin. Its corona, the tenuous outer atmosphere visible as a pearly halo during total solar eclipses, reaches temperatures of 1 to 3 million Kelvin. The Sun's core, where fusion occurs, sits at approximately 15 million Kelvin, making it 500 times hotter than its surface. These are the three main zones of solar temperature, arranged counterintuitively from hot core to cooler surface to hotter atmosphere, which is a puzzle on its own. The background temperature of interstellar space, what would be measured by a thermometer far from any star, is 2.725 Kelvin, as determined by precision measurements of the cosmic microwave background. This is not the temperature of interstellar gas clouds, which can range from 10 Kelvin in cold, dense molecular clouds to 10,000 Kelvin in warm ionized hydrogen regions. It is the temperature of the radiation field that permeates the universe, the ambient glow of the cosmos that everything in the universe is constantly bathed in. The Moon demonstrates what happens when a rocky body sits in space with no atmosphere to moderate these extremes. On the lunar day side, near the equator, surface temperatures climb to roughly 120 degrees Celsius, above the boiling point of water at standard pressure. On the lunar night side, with no atmosphere to trap any warmth, temperatures drop to around minus 170 degrees Celsius during the long lunar night, and to minus 240 degrees or colder in permanently shadowed craters near the poles. The total range, from day to night, spans close to 400 degrees Celsius, and the transition between them is not gradual. The terminator, the line dividing lunar day from lunar night, is a sharp thermal boundary with essentially no transition zone at all, because there is no air to carry heat from one side to the other. The International Space Station orbits at about 400 kilometers, alternating between sunlit and shadowed phases every 45 minutes. External surfaces facing the Sun can reach 120 degrees Celsius. The same surfaces facing away from the Sun and the Earth can fall to minus 150 degrees Celsius. That 300-degree range repeats 16 times per day, every day, and is why spacecraft thermal engineering is one of the most demanding disciplines in the field. Parker Solar Probe, which in December 2024 passed within 6 million kilometers of the surface of the Sun, closer than any previous human-built object, provides the most extreme illustration. The sun-facing side of its carbon composite heat shield reached temperatures approaching 900 degrees Celsius. On the instrument side of that shield, protected from direct radiation, temperatures hovered near room temperature. The two faces of a heat shield separated by a few centimeters of carbon foam experienced a temperature difference greater than 800 degrees. And around the spacecraft, the Sun's million-degree corona was causing essentially no additional threat to the instruments. Not because the corona was cool, but because it was so sparse that despite its extreme particle velocities, it contained very little total thermal energy. The distinction between particle speed and thermal energy density is a subtlety the corona makes unavoidable. There is a practical illustration of this same principle much closer to home. Earth's own upper atmosphere, the thermosphere, which extends from about 80 to 600 kilometers in altitude, technically has temperatures exceeding 1000 degrees Celsius when those temperatures are defined as the mean kinetic energy of its particles. The space station orbits within the uppermost reaches of the thermosphere, and yet the station is not incinerated by a 1000-degree atmospheric layer. The density of the thermosphere at orbital altitudes is so vanishingly thin, roughly 10 trillion times less dense than the air at sea level, that collisions with thermospheric molecules contribute negligibly to the spacecraft's thermal budget. The station is heated far more powerfully by direct solar radiation falling on its external surfaces than by anything the surrounding atmosphere does. The temperature of the thermosphere is technically high, the thermal energy it can exchange with a spacecraft is effectively zero. This is the same distinction that protects Parker Solar Probe in the solar corona, and it is one of the central physical lessons of the temperature story. How hot a gas is and how much heat it can transfer to a solid object are two entirely separate questions, and the answer to the second depends entirely on the gas's density. The solar wind. Space is not quite empty. Before leaving the subject of the sun's energy output, it is worth noting that the sun does more than radiate photons. It also continuously streams a flow of charged particles, electrons, protons, and helium nuclei, primarily, outward through the solar system in every direction. This flow is called the solar wind, and it was first predicted by Eugene Parker in a 1958 paper, the same Parker whose name the solar probe bears, at a time when most physicists assumed that interplanetary space was essentially static. Parker's prediction was controversial enough that his paper was initially rejected by reviewers who thought the idea was implausible. Direct measurements from early spacecraft confirmed its existence within a few years. The solar wind has been blowing continuously for as long as the sun has existed. The solar wind is not hot in the sense that its density is high enough to transmit meaningful heat. Near Earth, the solar wind contains roughly 5 to 10 particles per cubic centimeter, moving at speeds of roughly 400 to 700 kilometers per second. At these speeds, the particles have kinetic energies corresponding to temperatures of roughly 100,000 Kelvin. But because there are so few of them, the total amount of thermal energy they carry is negligible compared to the energy in the photons of sunlight. The solar wind cannot cook a spacecraft the way direct sunlight can. Its particles simply do not carry enough total energy to heat a surface significantly. The danger it poses is different. High-energy particles can damage electronics and biological tissue through radiation effects, not heating. The solar wind carves out a bubble within interstellar space called the heliosphere, a vast region within which the sun's influence dominates. This bubble extends well beyond the orbit of Neptune, beyond even the Kuiper belt, to a boundary called the heliopause, where the solar wind is finally stopped and turned back by the pressure of the interstellar medium. Voyager 1 crossed this boundary in August 2012 at a distance of about 121 astronomical units from the Sun. Voyager 2 crossed it in November 2018 at a slightly different distance of about 119 astronomical units, providing the first direct comparison of the heliosphere's boundary from two different directions. Outside the heliopause lies the interstellar medium, the thin gas and dust that fills the space between stars in our galaxy. The interstellar medium is not uniform. It ranges from hot, tenuous, ionized gas in the so-called hot interstellar medium at temperatures of roughly 1,000,000 Kelvin to warm neutral hydrogen gas at around 6,000 Kelvin, to cold dense molecular clouds at temperatures as low as 10 Kelvin. The Sun and its planetary system are currently traveling through a region of relatively warm, partly ionized gas called the local interstellar cloud, which has a temperature of around 6,000 Kelvin and a density of roughly 1 particle per 10 cubic centimeters. This is the environment just beyond our solar system's boundary, warmer than the CMB, but less energetic than anything in the inner solar system. As with the corona, the high temperature of the interstellar medium does not translate into significant heat transfer to objects moving through it. The density is simply too low. All of this, the solar wind, the heliosphere, the transition to interstellar space, represents a progression from the Sun's intense, organized outflow of energy through zones of decreasing density and decreasing direct solar influence, until finally reaching the vast interstellar ocean where the Sun's contribution is negligible, and the CMB's 2.725 Kelvin represents the ambient condition. Space is not uniformly cold between the Sun and the stars. It grades from hot and energetic near the Sun through progressively thinner environments until reaching the cold floor of the cosmic background. Earth's atmosphere, the great exception. Understanding why space is cold makes the warmth of Earth look increasingly miraculous. Earth occupies a position in space where the Sun's radiation delivers about 1,360 watts per square meter to the top of the atmosphere, about the output of a large hairdryer spread over each square meter of surface facing the Sun. This is the same flux that exists in nearby space, and on its own it would produce extreme temperature contrasts between the sunlit and shaded hemispheres, much as the Moon experiences. Instead, Earth is wrapped in an atmosphere that performs an extraordinary thermal service. The atmosphere absorbs, scatters, and re-radiates incoming solar energy in ways that dramatically reshape its distribution. Some solar energy is reflected directly back to space by clouds, ice, and bright surfaces. About 30% of the incoming solar radiation never reaches the surface at all. The rest penetrates to the ground and oceans, where it is absorbed and converted into thermal energy. But the ground does not keep this energy forever. It radiates it back upward as infrared radiation, heat radiation. And here the atmosphere intervenes again. Greenhouse gases, particularly water vapor, carbon dioxide, and methane, are largely transparent to incoming visible light but absorb outgoing infrared radiation. They re-radiate this absorbed energy in all directions, including back toward the surface, trapping heat in the lower atmosphere. This is the natural greenhouse effect, a process that raises Earth's average surface temperature from the -18 degrees Celsius it would otherwise be, a permanently frozen planet with all its oceans locked in ice, to the 15 degrees Celsius of the current world. The greenhouse effect is not a uniform blanket. Different greenhouse gases absorb different infrared wavelengths. Water vapor is the most abundant and the most powerful greenhouse gas by volume, responsible for more than half of the natural greenhouse warming. Carbon dioxide, though present in far smaller concentrations, absorbs infrared wavelengths that water vapor misses, filling in gaps in the infrared absorption spectrum and adding its own contribution to the total warming. Methane is a much more potent absorber per molecule than carbon dioxide, though it is present in smaller quantities. The combined effect of these gases produces an atmosphere whose infrared opacity is substantially greater than any single gas alone could achieve. The physics is one of the most precisely studied problems in atmospheric science, because accurately modeling the greenhouse effect is essential to any honest account of climate change. But the fundamental mechanism, gases that trap outgoing infrared radiation and warm the surface beyond what direct solar heating alone would produce, is thermodynamics that has been understood for over a century. Above this greenhouse layer, the atmosphere does not simply end. It grades through the stratosphere, where ozone absorbs ultraviolet radiation and creates a temperature inversion that makes the stratosphere warmer at the top than at the bottom. Through the mesosphere, where temperatures fall again. Through the thermosphere, where the sparse air is heated directly by X-ray and ultraviolet solar radiation to temperatures that technically exceed 1,000 degrees Celsius, but where the density is so low that an unprotected human would feel no warmth. Demonstrating, at a much smaller scale than the corona, but by the same principle, that high particle temperature and high thermal energy content are not the same thing. Finally, above the thermosphere lies the exosphere, where the atmosphere grades imperceptibly into the vacuum of space. The transition from a fully terrestrial atmosphere to true space is not a sharp boundary, but a gradual thinning that spans hundreds of kilometers. The circulation of heat within the lower atmosphere, the troposphere, where weather occurs, is driven by the very temperature gradients the sun creates. The equatorial regions receive more solar radiation per unit area than the poles, because sunlight strikes the tropics nearly straight down but strikes the poles at a steep angle, spreading the same amount of energy over a larger area. This creates a persistent temperature difference between equator and pole, and the atmosphere continuously works to eliminate it. The trade winds blow consistently from the subtropical highs toward the equatorial low, carrying heat equatorward. The jet streams circulate heat toward the poles. Hurricanes and extratropical cyclones are enormous heat engines that carry energy poleward in bursts of dramatic violence. The entire global circulation is a thermodynamic response to the uneven distribution of solar energy across the planet's curved surface. Above this rotating atmosphere of weather and wind, the behavior of clouds adds a further layer of complexity. Low-level clouds reflect solar radiation back to space, cooling the surface. High-level cirrus clouds trap outgoing infrared radiation, warming the surface. The net effect of clouds on Earth's energy balance is a topic of ongoing research and significant uncertainty, because the balance between these competing effects depends on cloud altitude, thickness, and coverage in ways that are difficult to model precisely. What is not uncertain is the basic physics. Clouds are players in the thermal regulation of a world that uses every available atmospheric mechanism to stay warm. None of these moderating systems operate in space. There are no greenhouse gases to trap heat, no oceans to store it, no winds to redistribute it. The Moon has no such layers, which is why its surface temperatures swing through nearly 400 degrees Celsius between day and night. Mars has a thin atmosphere that provides a very modest greenhouse effect, lifting its average surface temperature by about 10 degrees Celsius, but not nearly enough to allow liquid water to persist at the surface under current conditions. Venus, on the other extreme, has an atmosphere so dense with carbon dioxide that its greenhouse effect raises the surface temperature to 465 degrees Celsius, hotter than Mercury, despite being nearly twice as far from the Sun. The temperature of a planetary surface is not determined by distance from the Sun alone. It is determined by the interaction of solar radiation with whatever atmosphere that world happens to possess. Earth's particular combination of distance, atmospheric composition, and ocean coverage has produced a thermal environment without parallel in the known solar system. The Sun's own paradox, the coronal heating problem. The logic of why space is cold leads naturally to an uncomfortable question. If matter cools as you move it farther from a heat source, why is the Sun's own atmosphere violating this rule so dramatically? The corona sits above the photosphere, farther from the nuclear furnace below, and yet it is 200 to 500 times hotter than the surface it surrounds. This is not a small discrepancy. It is a fundamental violation of naive expectation that has demanded explanation for over 80 years without yet receiving a fully satisfactory one. The puzzle first crystallized during a total solar eclipse in 1869, when astronomers observing the corona noted a bright emission line in its spectrum at a wavelength that matched no known element. They named the responsible element coronium, assuming it was something new. 43 years later, During subsequent eclipses and laboratory analyses, another mysterious coronal line was identified. Slowly, the catalogue of coronium lines grew, and the assumption that they represented new elements became increasingly strained. In 1942, the Swedish spectroscopist Bengt Edlén resolved the mystery in a way that created a much deeper one. He demonstrated that the mysterious lines were not from new elements at all. They came from known elements, principally iron, that had been stripped of an extraordinary number of electrons. The specific line that had been puzzling astronomers for 70 years came from iron atoms that had lost 13 of their 26 electrons. Stripping that many electrons from iron requires temperatures exceeding 1 million Kelvin. The Sun's outer atmosphere was not merely hot, it was 170 times hotter than the surface below it, and the reason for this was entirely unknown. The second law of thermodynamics makes the situation peculiar in a specific way. That law states, in one common formulation, that heat flows spontaneously from regions of higher temperature to regions of lower temperature, never the reverse. If the corona is hotter than the photosphere is not directly heating it. Heat would flow the wrong way. Some other form of energy must be reaching the corona and being converted to heat there. The question is what? Solar physicists have converged on two broad categories of mechanism. The first involves waves, specifically magnetohydrodynamic waves propagating along the Sun's magnetic field lines. The Sun's surface is not placid. It churns with convective cells called granules, roughly the size of Texas, where hot plasma rises to the surface, spreads outward, cools, and sinks again in a constantly cycling pattern. This turbulent motion stresses and deforms the magnetic field lines that thread through the solar surface, generating waves that travel upward along those field lines into the chromosphere and corona. Alfvén waves, a particular type of magnetohydrodynamic wave named for the Swedish physicist Hannes Alfvén, who theorized their existence, can carry enormous amounts of energy. Observations from the Solar Dynamics Observatory and the Solar Orbiter spacecraft have confirmed that Alfvén waves in the corona carry energy fluxes large enough to account for the coronal temperature. But the mechanism by which waves break down and deposit their energy as heat in the sparse coronal plasma has not been definitively established. Waves can propagate over long distances without efficiently transferring energy to the medium they move through. Finding the dissipation pathway is the critical, unsolved step. The second mechanism involves what the American physicist Eugene Parker, proposing the idea in 1987, called anoflares. Parker observed that the Sun's magnetic field lines are constantly being braided and tangled by the turbulent convective motions below the surface. When field lines of opposing polarity are pressed together sufficiently, they undergo magnetic reconnection, a process in which the opposing lines snap and join in a new configuration, releasing stored magnetic energy as a burst of kinetic and thermal energy. Parker calculated that if this process occurred at tiny scales across the entire surface of the Sun, millions of small events per second, each releasing energy comparable to a small hydrogen bomb, the cumulative effect could maintain the corona at million-degree temperatures. The events he proposed were far too small to detect with instruments available in the 1980s, which was part of why the idea remained hypothetical for decades. In July 2020, the ESA/NASA Solar Orbiter spacecraft returned its first close-up images of the Sun's surface and revealed tiny brightenings scattered across the solar disk. Structures the science team called campfires. These campfires were far smaller than any previously resolved solar events, and their properties were consistent with nanoflare-scale magnetic reconnection events. Precisely as Parker had predicted, they were not direct proof of nanoflares, but they were the first observational evidence that small-scale reconnection events of roughly the right character were occurring with roughly the right frequency to matter for coronal heating. The Parker Solar Probe has been probing the corona directly since 2018, progressively approaching the Sun through a series of orbits modified by Venus gravity assists. Each close pass has taken the probe deeper into the corona and gathered data at resolutions and distances that no previous mission could reach. In July 2024, researchers at the University of Michigan used Parker data to rule out one of the leading candidate mechanisms. S-shaped bends in the Sun's magnetic field, called switchbacks, had been proposed as potential energy conduits to the corona. But the probe's measurements showed that these structures do not form in the corona itself. They must form farther out, making them unlikely contributors to coronal heating. The December 2024 perihelion, the probe's closest ever solar pass at a speed of 690,000 kilometers per hour, placed instruments deeper inside the corona than any spacecraft had ever reached. The data from that pass is still being analyzed. The coronal heating problem remains one of the most conspicuous open questions in all of astrophysics, an embarrassment of proximity. We cannot fully explain the atmosphere of the nearest star. The cosmic microwave background, where the cold actually comes from. When astronomers state that the background temperature of space is 2.725 Kelvin, they are not saying the vacuum has a temperature. They are describing the energy of a specific type of radiation that permeates the universe uniformly and from all directions, and that carries the fingerprint of the universe's earliest accessible history. This radiation is the cosmic microwave background, and its existence and its temperature are among the most profound facts in cosmology. The discovery was inadvertent and initially baffling. In 1964, Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, using a large horn-shaped antenna that had originally been built to receive signals from the ECHO satellite. They were attempting to use it as a precision radio telescope, and they were frustrated by a persistent, uniform background noise that they could not explain or eliminate. The noise was the same in all directions. It was equally present at all times of day and all seasons. It did not correlate with any astronomical source they could identify. They were so determined to eliminate it that they dismantled parts of the antenna system, re-examined all of their calibration procedures, and evicted a pair of pigeons that had been roosting inside the horn and fouling the interior surfaces. They politely described the residue as white dielectric material. After all of this, the noise remained. What they had accidentally stumbled onto was the oldest light in the observable universe. At Princeton, just 50 kilometers away, a team of physicists led by Robert Dicke had been preparing to search specifically for this radiation, based on a theoretical prediction that the universe's violent early history should have left behind a thermal relic. When Penzias and Wilson heard about the Princeton group's project and the two groups compared notes, the explanation became clear immediately. Penzias and Wilson had found what Dicke's team had been looking for. The two sets of scientists published companion papers, one reporting the detection, one providing the theoretical interpretation, in 1965. Penzias and Wilson received the Nobel Prize in Physics in 1978 for their discovery. To understand what they had found, it is necessary to go back much further than 1965. In the first few 100,000 years after the Big Bang, the universe was not the largely empty, transparent space we inhabit today. It was a dense, opaque plasma, a soup of free electrons, protons, and photons so tightly coupled that light could not travel freely. The photons were constantly being scattered by the free electrons, which meant they could not move in straight lines. They were trapped in a kind of dense fog, bouncing around in the plasma and unable to escape. The universe in this early era glowed like the inside of a star, uniformly bright, opaque, and intensely hot. As the universe expanded over those first hundreds of thousands of years, it cooled. When the temperature fell to around 3000 Kelvin, about 380,000 years after the Big Bang, something critical happened. Electrons and protons, which had previously been too energetic to stay bound together, were suddenly cool enough to combine and form neutral hydrogen atoms. The fog lifted. The universe became transparent almost instantaneously on cosmic timescales, as the free electrons that had been scattering photons were absorbed into atoms. The photons that had been trapped in the plasma were suddenly free to travel through space unimpeded. They have been doing so ever since. In the nearly 14 billion years since that moment, the universe has expanded enormously. All those free-traveling photons from the moment of recombination, the moment the universe turned transparent, have had their wavelengths stretched continuously by the expansion of space, a process called cosmological redshift. What began as photons with wavelengths in the infrared and orange-red visible spectrum, corresponding to a temperature of 3000 Kelvin, have been stretched by a factor of about 1000. Today, they peak at microwave wavelengths corresponding to a temperature of 2.725 Kelvin. They permeate the universe uniformly in all directions, arriving at Earth from every point in the sky, each photon having traveled almost 14 billion years since its last interaction with matter. There are, according to the best measurements, approximately 400 of these cosmic microwave background photons in every cubic centimeter of space in the universe, including the space inside your body right now, and the space of every room, building, ocean, and atmosphere on Earth. The universe is continuously bathed in this ancient light, so faint that it required a sensitive radio telescope to detect it, but so pervasive that there is nowhere in the universe it is not present. The 2.725 Kelvin temperature it represents is the true ambient condition of the cosmos, the floor of warmth left over from the Big Bang's heat, diluted across nearly 14 billion years of expansion to something barely above nothing. The theoretical framework for the CMB had been laid 2 decades before its detection. In 1948, Ralph Alpher and Robert Herman, working from George Gamow's calculations about the early universe, predicted that the Big Bang would have left behind exactly this kind of residual radiation and estimated its current temperature at around 5 Kelvin, remarkably close to the actual value. Their prediction went largely unnoticed for over a decade and a half, until Penzias and Wilson stumbled onto its existence with their pigeon-fouled antenna. Since its discovery, the CMB has been measured with extraordinary precision. NASA's Cosmic Background Explorer satellite, launched in 1989, made the first detailed all-sky maps and found that the CMB was a nearly perfect blackbody, more perfect, in fact, than any blackbody source physicists have been able to create in a laboratory. Its temperature is uniform to better than 1 part in 100,000 across the entire sky, with only the tiniest fluctuations imprinted on it. Fluctuations that reflect the slightly uneven distribution of matter in the early universe, the seeds from which all the galaxies and galaxy clusters we observe today eventually grew. COBE's principal investigators, John Mather and George Smoot, were awarded the Nobel Prize in Physics in 2006 for this work. NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, and the European Space Agency's Planck satellite, launched in 2009, refined these measurements further, producing maps of the CMB with exquisite sensitivity that have constrained the age, geometry, and composition of the universe with remarkable precision. This is why space is cold. Not merely because radiation can only warm what it strikes, but because the universe began in a furious blaze of heat that has been cooling ever since, and what remains of that original warmth is now so diluted and stretched that it barely registers on any instrument designed for ordinary temperatures. The universe is still cooling. The 2.725 Kelvin temperature of the cosmic microwave background is not a fixed constant of the universe. It has been falling since the moment of recombination, and it is still falling. The universe is expanding. The photons of the CMB are being stretched further, and the temperature they correspond to is decreasing proportionally. In a billion years, the CMB temperature will be around 2.5 Kelvin. In 10 billion years, it will be around 2.4 Kelvin. As the expansion of the universe is currently accelerating under the influence of dark energy, the rate of cooling will eventually increase, but the numbers remain close to absolute zero for so long that the practical implications for any hypothetical life in the distant future would be measured in degrees rather than orders of magnitude. The coldest object currently known in the universe illustrates how far some matter has already traveled below even the CMB temperature. The Boomerang Nebula, located about 5,000 light-years away in the constellation Centaurus, is a planetary nebula, the expanding remnant of a dying star that has shed its outer layers. Its central star has been driving an outflow of gas at extraordinarily high velocity, approximately 500,000 kilometers per hour, for about 1,500 years. As the gas expands and accelerates, it cools through adiabatic expansion, the same physical process that chills the air when it escapes from a pressurized container. The cooling has been so extreme that the Boomerang Nebula has reached a measured temperature of approximately 1 Kelvin, colder than the cosmic microwave background itself. It has, in effect, used the energy of stellar outflow to cool itself below the ambient temperature of the universe, creating a transient pocket of cold more extreme than anything else in the natural universe. It is an anomaly, a fleeting achievement in cosmic terms, and it will eventually warm back to equilibrium as the expansion slows and the gas distributes its energy. Temperatures at the other extreme of the cosmic range are equally staggering. The hottest natural environments in the universe are the interiors of the most massive stars in their final moments before collapse. During a core collapse supernova, temperatures in the collapsing stellar core can briefly reach hundreds of billions of Kelvin as the infalling material compresses and rebounds. The jets produced by the most energetic quasars, which are supermassive black holes actively consuming surrounding gas, contain plasma at temperatures in the low trillions of Kelvin. The extreme particle accelerator events in the jets of blazars, where relativistic plasma is flung outward along magnetic field lines, produce particle energies equivalent to temperatures that strain even scientific notation. And then there is the beginning. The early universe itself, in the fraction of a second after the Big Bang, existed at temperatures that dwarf everything that has come since. At 1 microsecond after the Big Bang, the temperature was around 10 trillion Kelvin. At 1 millisecond, around 1 trillion Kelvin. At 1 second, it had already fallen to around 10 billion Kelvin, still hotter than the core of any star that exists today. The universe has been cooling for 13.8 billion years, from that original extremity of heat to the 2.725 Kelvin background, and the patchwork of warm stars scattered through the cold void that constitutes the cosmos we inhabit. Between the moment the CMB was released, when the universe turned transparent at 380,000 years, and the ignition of the first stars, there was an epoch known to cosmologists as the Cosmic Dark Ages. During this period, the universe contained no stars, no galaxies, no black holes, and no sources of light. It was permeated only by the CMB photons, cooling as the universe expanded, and by a gradually assembling fog of neutral hydrogen gas that was slowly gravitationally pulling together into the filaments and clumps that would eventually form the first galaxies. The universe was, for a period estimated at somewhere between 100 and 200 million years, not merely cold but dark, truly dark in every direction, with no source of photons beyond the fading afterglow of the Big Bang itself. The CMB at that time had already cooled to temperatures of a few tens of Kelvin, approaching the floor. There were no observers to see any of it, because there were no stars to make any of the elements heavier than hydrogen and helium from which observers are eventually built. The Dark Ages ended with the formation of the first massive stars, objects many times more massive than anything in the present universe, which ignited in a blaze of ultraviolet radiation intense enough to reionize the surrounding hydrogen gas and literally light the universe up for the first time. The epoch of reionization, as this process is called, is one of the most important and least understood transitions in cosmic history, and its detection and characterization is one of the primary scientific targets of the James Webb Space Telescope and the upcoming generation of ground-based, extremely large telescopes. The universe is, on the whole, very cold and becoming colder. The few 100 billion stars currently shining are bright exceptions in an ocean of freezing dark. Their combined luminosity, impressive as it is, heats only a tiny fraction of the cosmic volume. The rest, the voids between galaxy clusters, the intergalactic medium, the regions of space more than a few light years from any star, sits at temperatures indistinguishable from the CMB floor, essentially at the ambient temperature of a universe that has been cooling since the Big Bang and will continue cooling until the last source of heat has gone dark. The second law and why. Cold Findi in the end. What makes space so cold, and what will make it colder still, is the direction in which thermodynamics operates. The second law of thermodynamics is one of the most powerful and inescapable principles in all of science. In its everyday formulation, heat flows spontaneously from hot objects to cold ones, never the reverse. In its more fundamental formulation, in any isolated system, entropy, the measure of disorder or the number of accessible microscopic states, always increases over time. The universe moves toward greater disorder, greater uniformity, greater equilibrium. It does not, of its own accord, spontaneously organize into lower entropy configurations. Applied to the cosmos as a whole, the second law has a stark implication. The universe began in a state of extraordinarily low entropy, compact, dense, hot, and highly organized. Everything since then has been a process of entropy increasing, matter organizing under gravity into stars and planets, those stars burning through their nuclear fuel and converting organized energy into dispersed radiation, that radiation spreading through space and losing its ability to do further work. Every star that burns is using up ordered, low entropy energy and converting it into higher entropy, more disordered radiation. Every process that generates warmth, light, or complexity does so by consuming the available energy gradients that make those processes possible. And those gradients are finite. In the far, far future, on timescales so vast that describing them requires powers of 10 that are themselves astronomical, the available energy gradients will be exhausted. Stars will have consumed all the hydrogen and helium available for fusion in galaxies. White dwarfs, the cold remnants of stars like the Sun, will cool over trillions of years toward the ambient temperature of the universe. Neutron stars will radiate their heat into the cold void. Black holes will gradually evaporate through a quantum process called Hawking radiation, the most drawn-out process in the known universe, taking estimated timescales of 10 to the power of 100 years for the most massive black holes to evaporate completely. When the last black hole has finally radiated away its mass, what remains will be an extremely diffuse cloud of fundamental particles and very low-energy photons at a temperature so close to absolute zero that the difference becomes negligible. This endpoint is called the heat death of the universe, or sometimes the Big Freeze. The name heat death is counterintuitive, since it implies a cold rather than a hot final state. The term comes from the thermodynamic concept of maximum entropy, which is sometimes described as a state of uniform heat. But in the context of a cooling, expanding universe, maximum entropy approaches, but never quite reaches, absolute zero. The temperature will asymptotically approach zero without ever arriving there, because the third law of thermodynamics states that absolute zero cannot be reached in a finite number of steps. The universe will not end in a snap. It will fade away incrementally over timescales that the human mind has no purchase on. The heat death hypothesis was first articulated by the Scottish physicist William Thomson, later known as Lord Kelvin, in 1852, when he observed that mechanical energy is continuously being converted into heat through friction and irreversible processes, and that this must eventually produce a state where no further useful work is possible. Hermann von Helmholtz made the extension to a universal context explicit. In the late 19th century, the full implications of entropy were not entirely clear, and the idea of the universe running down seemed almost too final to take seriously. It is now considered the most likely fate of the universe, given current cosmological models, and the evidence from dark energy, the mysterious force accelerating the universe's expansion, suggests that the heat death scenario, rather than alternatives like the Big Crunch, is indeed where cosmology points. Cold, then, is not just the current condition of most of the universe. It is its destination. What we live in now, with the sun blazing and Earth warm and 100 billion other stars burning throughout the galaxy, is a temporary exception. A brief episode of thermodynamic richness in a universe that was fiery at its birth, is cooling steadily, and will end in the deepest cold that nature permits. The vacuum of space is cold precisely because it receives almost nothing. Far from any star, there is no energy being deposited into the void. The few particles that exist there, 1 or 2 hydrogen atoms per cubic centimeter, on average, in the space between stars, move at speeds corresponding to temperatures of a few thousand Kelvin in some regions and far lower in cold molecular clouds. But they are so sparsely distributed that they carry essentially no heat in any practical sense. A human hand plunged into deep space would not be chilled by those particles. They are so rare that collisions with them would be negligible. What the hand would experience instead is the slow radiative loss of its own warmth into the void. The gradual departure of its heat as infrared radiation emitted into a surrounding environment so cold that almost no radiation returns to replace it. It would take longer to cool this way than most intuition suggests, because thermal radiation at body temperature is not spectacularly efficient. But the hand would cool steadily and irreversibly until it reached thermal equilibrium with the surrounding radiation field, which is to say, until it had cooled to just above absolute zero. The gradient between the Sun's blazing core and the cold void of interstellar space is also what drives the stellar life cycle itself. Stars exist because gravity compresses hydrogen gas into a dense enough configuration that nuclear fusion ignites, generating the outward pressure that prevents further collapse. Stars live for as long as the balance between gravitational compression and radiation pressure can be maintained. When the hydrogen in the core is exhausted, the balance shifts. The core contracts and heats further, while the outer layers expand and cool. A star like the Sun will eventually swell into a red giant, its outer atmosphere expanding outward to engulf the inner planets, while the remaining core contracts into a white dwarf. A dense remnant, roughly the size of Earth, that will spend trillions of years radiating its heat into space, cooling so slowly that even after the age of the current universe has passed several times over, white dwarfs formed today will still be warm enough to faintly glow. Massive stars follow a more violent course. Their greater mass means greater gravitational pressure, which drives higher core temperatures, faster fusion, and much shorter lifespans. Some live only a few million years, a cosmic eye blink compared to the Sun's 10 billion year main sequence lifetime. When a massive star's core finally collapses, the resulting supernova can briefly outshine an entire galaxy of hundreds of billions of stars, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. The shockwave of this explosion heats the surrounding interstellar medium to tens of millions of Kelvin, creating hot bubbles of plasma that gradually cool over thousands of years as they expand. The heavy elements forged in the star's core, carbon, oxygen, iron, gold, uranium, are scattered across light years of space, eventually mixing with cooler gas and dust to form new molecular clouds. From those clouds, given enough time and the right conditions, new stars and planets form. The atoms in your body were once inside a star, heated to temperatures tens of millions of degrees, and they are now arranged in patterns complex enough to be asking questions about temperature in the universe. Every process in this chain, nuclear fusion, convection in stellar interiors, the outward radiation pressure that gives stars their stability, the explosive deaths that scatter heavy elements, the cooling of stellar remnants over eons, is a thermodynamic process driven by the existence of temperature gradients. The universe creates gradients through gravity, and matter flowing down those gradients, energy moving from hot to cold, is the engine that runs everything. Stars are local concentrations of heat in a cold universe. Their light and warmth are not permanent gifts. They are the sound of energy flowing downhill, of temperature differences being consumed, of the universe steadily approaching the equilibrium it will eventually reach. Temperature at every scale. The view from the smallest and largest. The story of heat and cold in the universe connects scales from the subatomic to the cosmological in a way that reveals the underlying unity of thermal physics. At the very smallest scales, quantum mechanics places a fundamental limit on how precisely temperature can even be defined. Absolute zero is not just experimentally unattainable, it is, in a precise quantum mechanical sense, impossible to reach even in principle. The Heisenberg uncertainty principle ensures that particles always retain some residual energy, or zero-point energy, even at the lowest achievable temperature. This energy cannot be removed, because doing so would require knowing the precise position and momentum of every particle simultaneously, which quantum mechanics forbids. In practice, the coldest temperatures ever achieved by humans have been produced not in outer space, which, despite its cosmic coldness, lacks the infrastructure for extreme cooling, but in laboratories on Earth. In 2021, researchers created a Bose-Einstein condensate of rubidium atoms that, for a brief moment, reached a temperature of 38 picokelvin, 38 trillionths of a Kelvin, more than 100 billion times colder than the cosmic microwave background, and the coldest temperature ever measured. These experiments require not simply removing heat, but using laser cooling and magnetic trapping techniques to bring atomic motion to a near standstill, exploiting the same quantum effects that set the lower limit on temperature in the first place. At such temperatures, quantum effects dominate completely, and matter behaves in ways that have no counterpart in ordinary experience. None of this extreme cold exists in nature. Nature produces Bose-Einstein condensates only in hypothetical future scenarios involving very cold planetary systems around dying stars over timescales that dwarf the current age of the universe. The coldest natural object known, the Boomerang Nebula, at approximately 1 Kelvin, is far warmer than what human ingenuity has achieved in a laboratory. This inversion, in which the products of human technology are colder than the coldest natural object in the observable universe, is a strange consequence of the controlled conditions possible in a terrestrial laboratory. Nature rarely cools matter below the CMB floor. Doing so requires work and organization that natural processes do not spontaneously supply. Temperature, then, is not a simple ladder from cold to hot. It is a property that emerges from motion, is shaped by the nature and density of matter, is transferred through physical mechanisms that require specific material conditions, and is governed by thermodynamic laws that impose a direction on all physical processes in time. Space is cold, not because the universe is naturally cold, but because the energy that exists in the universe is distributed in extraordinary contrast, concentrated in the dense, hot interiors of stars, and essentially absent in the vast spaces between them. Those contrasts are what make energy flow, and energy flow is what makes everything interesting that has ever happened in the universe. Spacecraft survival, engineering at the intersection of cold and hot. The extreme temperature contrasts of space are not only scientifically interesting, they are an engineering obstacle that every human space mission must solve. Every spacecraft launched beyond Earth's protective atmosphere must survive the simultaneous threats of intense solar radiation on its sun-facing sides, and the near-total absence of heat input on its shaded sides, with nothing but thermal radiation as the only mechanism for either gaining or losing heat. The discipline this generates is called thermal control engineering, and it shapes spacecraft design in ways that are rarely visible to the public, but are absolutely fundamental to mission success. The basic problem is this: electronics, sensors, and batteries all have operating temperature ranges. A lithium-ion battery that works well at room temperature will fail below about -20 degrees Celsius and above about 60 degrees Celsius. Solar cells have optimal performance at specific temperatures. Optical instruments need their mirrors and lenses to maintain precise shapes, which means their temperatures must not vary too much. Lubricants in mechanical joints can freeze solid at temperatures common in outer space. Every component on every spacecraft has a thermal requirement, and the spacecraft's thermal control system must keep every component within its limits, despite an environment that might impose a temperature range of several hundred degrees on the spacecraft's exterior. Engineers address this through a combination of passive and active techniques. Passive thermal control uses the physical properties of surfaces, their emissivity, which determines how efficiently they radiate heat away, and their absorptivity, which determines how efficiently they absorb solar radiation. By coating different surfaces of a spacecraft with different materials, engineers can tune how the vehicle exchanges heat with its environment. Multi-layer insulation blankets, consisting of many thin layers of metallized plastic film separated by thin mesh spaces, reduce radiative heat exchange by building up a stack of reflective surfaces that each intercept and re-emit a portion of the incoming or outgoing radiation, dramatically reducing the net heat flow. Gold-colored spacecraft surfaces, familiar from countless photographs, reflect solar radiation efficiently while emitting very little infrared radiation, keeping the surface cool in sunlight. Black surfaces, used for radiators on the shaded side, emit infrared radiation efficiently, cooling the components they are connected to by radiating heat into the cold sky. The challenge becomes far more dramatic in the outer solar system. The New Horizons probe that flew past Pluto in 2015 receives less than 1,000th of the solar energy per square meter that Earth does. The Sun from Pluto is barely brighter than a very bright star. Its instruments must stay functional at temperatures near -220 degrees Celsius, which means that unlike inner solar system missions, the primary thermal challenge is not managing excess heat, but preventing the spacecraft from freezing. The probe's electronics generate some waste heat from their operation, and New Horizons is designed to trap that heat internally rather than radiating it away. Essentially, the opposite thermal engineering philosophy of a spacecraft near the Sun. The interior of the spacecraft is thermally insulated from the cold exterior, and heaters keep critical components warm using electricity generated by a radioisotope thermoelectric generator. Even the choice of lubricants in mechanical joints had to account for extremely low temperatures. Conventional greases that flow easily at room temperature can become stiff or solid at the temperatures of the outer solar system. The Voyager probes, now in interstellar space, represent the ultimate test of thermal design longevity. Launched in 1977, they have been operating for nearly half a century in the coldest environment any human-built object has ever inhabited. Their engineering choices reflect the technology and knowledge of the 1970s, yet both probes are still transmitting meaningful science data. Their radioisotope thermoelectric generators, which convert the heat from radioactive plutonium decay directly into electricity, have been declining in output at roughly 4 watts per year as the plutonium depletes and the thermocouples degrade. By the mid-2020s, each probe had less than half its original power budget. Mission engineers have been making difficult choices about which instruments to shut down, prioritizing those that continue to return unique scientific value. Keeping any instrument operating in a spacecraft designed for a different era of power availability at temperatures far below what any terrestrial laboratory routinely achieves is an engineering achievement that sits at the intersection of physics and sheer determination. Active thermal control adds heating elements that warm instruments during periods of shadow, and cooling loops that carry waste heat from electronics to external radiators during periods of high solar loading. The International Space Station's thermal control system circulates ammonia coolant through internal loops that collect heat from crew activities electronics, and experiments and route it to external radiators. Those radiators, which are large panels mounted on the station's truss structure, reject the heat by radiating it into the cold shadow portion of the sky. The system must handle variable thermal loads as the station moves in and out of sunlight, as solar activity changes, and as the crew conducts experiments and exercises. The radiators are sized for the worst-case heat load, and the active thermal control system continuously adjusts coolant flow rates to maintain internal temperatures within acceptable ranges. It is an engineering response to the same physics that makes space cold. In a vacuum, radiation is the only heat transfer mechanism available. So every gram of waste heat must be removed by carefully managing what and how the spacecraft radiates. The James Webb Space Telescope, which began science operations in 2022, presents perhaps the most sophisticated thermal engineering challenge in the history of space astronomy. Webb needs its infrared detectors to be kept at temperatures near -230 degrees Celsius, about 40 Kelvin, to prevent the telescope's own thermal radiation from swamping the faint infrared signals from the distant universe. To achieve this, Webb is positioned not in Earth orbit, but at the second Lagrange point, about 1.5 million kilometers from Earth on the night side of the planet, where it can always point away from both the Sun and Earth. Its enormous 5-layer sun shield, roughly the size of a tennis court, keeps the telescope in permanent thermal shadow, shielding it from solar, Earth, and lunar radiation simultaneously. The warm side of the sun shield, facing the Sun, reaches temperatures around 85 degrees Celsius. The cold side, where the telescope sits, cools passively to around -230 degrees Celsius, purely by radiating heat into the cold, dark sky facing away from the Sun. No active cryocoolers are needed for the primary mirror and main detectors. The coldness of deep space, properly harnessed through careful geometry and surface engineering, does the job. Webb is, in this sense, a machine designed to exploit the coldness of space as a scientific instrument in its own right. What the question really teaches us: why is space cold when the Sun is so hot? The answer, pursued to its foundations, is a course in the physics of the universe. It begins with the distinction between temperature and heat, moves through the mechanics of heat transfer, establishes why vacuum supports only radiation, clarifies the Sun's energy output and its journey through 8 minutes of empty space, addresses the paradox of the hot corona and the 80-year mystery still surrounding it, reaches the cosmic microwave background and the universe's ancient thermal history, and arrives finally at the second law of thermodynamics applied to the fate of everything. Along the way, it forces engagement with what temperature actually means. Not an intuitive warmth or chill, but the kinetic energy of particles in a medium, a quantity that cannot exist without matter to carry it. It requires understanding why light, for all its energy, does not warm the vacuum through which it travels, and why the Earth is a peculiar exception maintained by an atmosphere and ocean that most worlds do not have. It reveals that the Sun itself, the dominant object in our solar system, has an outer atmosphere that defies simple thermal logic, and has been doing so for 80 years without anyone finding a complete explanation. And it demonstrates that even the engineers who build our spacecraft are in constant negotiation with these same forces, designing every surface coating and every coolant loop around the fundamental reality that space gives heat nowhere to go except outward, by radiation, into an environment that will absorb it without ever being warmed. One of the things the question also teaches is how deceptive human perception is when applied to physics. We feel the sun's warmth and assume that warmth must be everywhere the sun's light reaches. We stand in space, in imagination, in the mental model most people carry, and picture it like a very cold room, perhaps like standing outside on a winter night. But standing outside on a winter night is not like being in space at all. On a winter night, the air itself conducts and convects your body heat away from you, carrying it off on the breeze. The cold you feel on your skin is the absence of heat insulation, the removal of your body's warmth by moving air. In space, that mechanism does not exist. The cold of space is not active, it is passive. It is the absence of anything to interact with. Nothing is removing your heat. Nothing is pressing against you with low temperature molecules. Instead, you are simply emitting your own heat as radiation, slowly into a surrounding environment that is barely warm enough to give back almost nothing in return. Cold in space is not a force pressing in from outside. It is a vacuum pulling energy out from within, through the only channel available. This distinction matters beyond physics. It reflects something about the nature of cold and heat that is easy to miss in an atmosphere-wrapped world. We experience cold as an active presence, the chill of a winter morning, the bite of a cold metal surface, the sharp sting of ice. All of those experiences are the result of heat being actively drawn out of us by conduction and convection, by fast-moving molecules carrying our warmth away. But the cold itself is nothing. It is the label we put on the condition of low molecular energy. The universe does not generate cold the way the sun generates heat. Cold is simply what you get when heat has moved away and nothing has replaced it. The universe does not hate us or intend our discomfort. It is not cold because something made it cold in the way a refrigerator is cold because a compressor removed the heat. It is cold because most of the universe has never had a nearby source of energy. The heat of the Big Bang has been spreading and diluting for 13.8 billion years and will continue to do so. The energy that remains is concentrated in specific, extraordinary places. In stars, in the hot plasma of galaxy clusters, in the violence of quasar jets and supernova shockwaves. And between those concentrations lies the void, old and patient and almost entirely empty, carrying only the faint warmth of a universe's youth stretched to microwaves. And it ends somewhere genuinely unsettling, with the realization that the universe is cooling, that the warmth produced by stars is a transient feature of a cosmos that began in fire and is moving steadily toward a cold equilibrium, and that the comfortable temperature of the surface of this planet, the temperature that makes liquid water stable, that sustains chemistry, that makes life possible, is a local and temporary exception to the overwhelming coldness of the rest of the cosmos. None of this makes the warmth on a summer afternoon less real. It makes it more extraordinary. The sun has been generating the energy that warms this world for nearly 5 billion years. It will continue doing so for roughly 5 billion more. The temperature gradient it maintains, the steep descent from the sun's 15 million Kelvin core through the cool void of space to the carefully moderated surface of this planet, is the engine that drives every weather system, every ocean current, every photosynthetic reaction, and every other energy-consuming process on Earth. Without that gradient, there would be nothing. With it, there is everything. Space is cold because most of the universe is empty and most emptiness has no energy source nearby. The Sun is hot because nuclear fusion concentrates energy into a tiny volume at immense pressure and temperature. Earth is warm because it sits at exactly the right distance from that furnace, wrapped in exactly the right gases, to capture and redistribute just enough of that energy to keep water liquid and chemistry running. That precise set of conditions, maintained for nearly 4 billion years, is why this question can be asked at all, and why the person asking it is warm enough to wonder. If you have stayed this long with a question that started in a summer parking lot and ended at the heat death of the universe, this channel has more where that came from. The cosmos does not run short of questions that sound simple and turn out to be doors into something vast. Subscribe and keep asking them with us.